This is a final video on colligative properties, and we're going to do calculations here on this. But before we do it, we have to define one term, and it's called the molality. And it's like the molarity, and they both have moles of solute on the top. But on this molality, we have kilograms of solvent. In molarity, over on the right, we have liters of solution on the bottom. So the difference in these is the bottoms of it, and you got to keep that in mind when you're doing these. All colligative properties go with molality, and so the two equations we're going to do is we'll start with boiling point elevation, and the equation for boiling point elevation is the change in temperature, delta T of boiling, is equal to I, and that's the Van Hoff factor, times K boil times the molality. Actually, they usually write it I M KF. Doesn't matter. Okay? And so we know how to calculate molality. That's straightforward. I is the number of ions if it's ionic, and it's 1 if it's a molecule that's dissolved. And K boiling is a constant that you will be given or asked to calculate. So I'm basically going to ask you to calculate one of these four things: the molality, K boiling, the Van Hoff factor, or the change in boiling point. So let's just do a simple problem. So here's our problem. Benzene boils at 80.1 degrees and has a K boiling of 2.53. This constant K boiling always goes with the solvent. It is solvent dependent, not solute, but only with the solvent. So what temperature will a solution of 30 grams of toluene, so I write that down, 30 grams of toluene, I'll just abbreviate it, which is C7H8, and 200 grams of benzene. I'll put a B in there. I also know Kb equal 2.53 degrees Celsius per molal unit, and I know that T boil for benzene is equal to 80.1. So I look at my equation, delta T boil equal I times K boil times the molality, and I'm going to calculate the molality because I have everything I need. I need the amount of the solute and the amount of solvent in blue here. Okay. And so I can calculate the molality over here. I have Kb. I know I is equal to 1. I'll write that down. My list of things. I equal 1 because it's a molecule. And I know it's a molecule because it's not a salt. Remember, salts are metals and nonmetals. Those are the only salts you have to worry about in this. So all I really have to do is calculate the molality. Then I can calculate the change in boiling temperature. So let's get the molality first. I have 30 grams of toluene. 30 grams of toluene times the molar mass of toluene, which you should know how to do. And so I'm not going to do that. It's 92.14 grams per mole. That gives us moles of C7H8 divided by grams, 92.14 grams of C7H8. And that gives me the moles of the solute. This is our solute, and our solvent is benzene, divided by 200 grams of benzene. I'll write it C6H6. And that is the molality. All I got to do is convert the grams of benzene to kilograms. So 1,000 grams of C6H6 per 1 kilogram of C6H6. That's the molal unit, moles per kilogram. And when I do that, I get molality, little m, equal 1.63, and my units are moles per kilogram of benzene, C6H6, and this is moles of C6H7 on the top. Okay, so now all I got to do is calculate delta T boiling. So this is usually a two-step process, and this is the kind of question, the one that I'm likely to ask you on the exam. So now we can do the second part. Delta T equal I times Kf times the molality. We know I equal 1. If we go back up here, that should be Kb down here. Kb equal 2.53 degrees Celsius per molal unit. And I have, over here, I have 1.63 molal units. And so the change in temperature will be 4.12 degrees Celsius. Now that's the change in temperature. And I know that benzene, because it was given, boils at, what was that temperature? 80.1. It boils at 80.1 is the normal boiling point, and it has to be 4.12 degrees Celsius above it. So 80.1 plus 4.12 degrees Celsius gives me 84.2 degrees Celsius. And that is the boiling temperature of that. That's one problem.